this video, I am going to show you how we can classify the images present in the Cipher10 dataset using a simple neural network. Cipher10 dataset is a dataset that is provided in the PyTorch library, and it consists of different classes of images. Basically, there are 10 classes of images which we need to classify. So the first task is to import all the libraries. I have imported the pandas, torch vision, torch, and matplotlib for plotting the graphs. The second task is to get the Cipher10 dataset. It is already in the torch vision dataset provided under the name of Cipher10. So we have just used that. We have downloaded the dataset. So first I would import the libraries, then I would get the dataset. Files are already downloaded and verified. I am currently connected to the GPU runtime, as we will be using PyTorch, so it will be required to run GPU. And then we will see the properties of the dataset. So the training dataset is basically consists of 50,000 images. The test dataset consists of 10,000 images. There are basically 10 different classes of images from 0 to 9, and the image dimensions is of 3 cross 32 cross 32, which means basically it is a RGB valued image and of a size 32 cross 32. And a simple image is of this kind, where the image value is 6. It belongs to the label flock. Then I have divided the dataset into test validation and training. I have used the batch size of 200 and I have used the validation as 5,000. So basically the training dataset is divided into 45,000 and validation is of 5,000. And the batch size is 200. That creates 225 different batches for training, 13 for testing, and 25 for testing and 13 for validation. Here is a simple example of all the images that are present in the dataset. I have shown basically 200 images here, and then I have connected to the GPU device. Basically, I have checked if the device's GPU is available or not, and then I have connected it to the GPU database, GPU device. And this is a small class that consists of methods to basically transfer the data from our current PC to the GPU server. And I have used the .to function, which transfers the data from this particular device to a GPU. And I have defined some input size, as the size of the input is 3 cross 32 cross 32. Size of output is 10. I have defined some basic functions to calculate the model accuracy, which basically checks whether the output labels are equal to the input labels or not, and it basically checks the predictions and provides us the output in the term of an accuracy measure. I have also created two different plots, one for the loss and other for the accuracy. And I have created a base class which contains basically 4 different methods. One is for training the batch. In this training the batch, I have provided a batch, and then I have calculated the loss basically using the cross entropy from the predictions and the input labels, and then I have returned the loss. Secondly, I have created a validation batch which basically calculates the loss and then checks the accuracy using the function that we have earlier defined, model accuracy here. Similarly, I have created a validation epoch which basically checks the validation after a particular epoch, and it basically what it does is it computes it sums up the different validation losses that we have acquired over a particular epoch, and similarly it combines the different accuracies that we have get in a particular epoch over different batches, and it returns the validation loss and the validation accuracy of a particular epoch. Lastly, I have created a print epoch and result function that basically prints a particular line showing the validation loss and the validation accuracy of particular epoch. Then I have created a simple neural network. Basically, it consists of 7 layers. I have also created one with a small size. So basically, first we will run our dataset on a small network. So I will remove these these 3 linear classes, and I will change the size to basically 128. Here I will do 64, 128. Okay, and basically I will remove this also because we only need the output of third layer, and I will change the activation function from ReLU to Sigma. Okay, I have already copied the above code and pasted here, so we do not have to basically write the whole code again and again. I will run this thing now. So the model is created. Now we will check the model. I have also created a function called get gradients, which takes the input as model parameters, model name parameters, and then it gets the gradient of a get the gradients of the layers, and then it calculates the average gradient, minimum and maximum gradient of a particular layer. If the gradients are not present, as there won't be in the first or initial layer, so it provides them zero values. And I have also plotted the gradients in the type of a bar graph, which consists of the maximum gradients, the average gradients. Minimum I have not plotted because it doesn't make any difference if we plot the maximum and the average gradient. Then minimum won't create much of a difference. And finally, I have created a function for evaluate model, which will basically call all the batches at a particular time, and it will validate the batches of validation and provide us the result. Similarly, I have created a fit model function, which basically fits the model. It takes input the learning rate, the model which we are trying to train, the training, validation, and the optimization function. So the current optimization function that I have used is the SGD, which is stochastic gradient descent. And then I have provided the optimization function with the model parameters that I have passed, and also the learning rate. Then I will get the initial gradients for each epoch, and for each batch in the train loader. I have calculated the loss over a particular batch, and then I have back propagated the loss while retaining the graph. Retaining the graph is I have used because I have to check the weights and the gradients after the particular loss is propagated to the input, and then I have to check whether the gradients have decreased from the initial from the previous value or not, or are they equal to the previous value or not. So for that we need retain graph. I have also used the optimizer step, which basically steps the optimizer, and then I have again used the get gradient function to get the next value of the gradients. Then I have calculated the difference between the next and the initial value, and if the difference is less than 10 to the power minus 10, then we can say that the gradients are not updating much, and then then at the layer which provides us the minimum difference, at that layer the gradients are starting to become zero to the previous layers also. So here initial, I have provided the value initial to next, and the next would be equal to 0 because for the next iteration we need to calculate the next again. And lastly, we have used the zero gradient function so that the optimizer doesn't change. And then we have evaluated the model and returned the history or the particular result of the model. I will run this cell also. Here it is. So then I will transfer the train, validation and the test to the device. Then I will check the model. The initial model that we have created consists of 3 different layers. Here it is. The first layer is a linear layer of input 128. Second layer is a linear layer of 164. Third layer is a linear layer of 6010, basically the size of the output. Then different classes, and the activation function that we have used is Sigma. Now these are the model parameters. It basically consists of 402 to 250 model parameters that need to be trained, and the initial history over the particular validation loader is giving us an accuracy of about 10%. Okay, then I will run the sigmoid activation function with 50 epochs and a learning rate of 0.001. Basically, to show the working, I will run it on 10 epochs only, so that it saves some time. It will take some time to run on the data. So after the first epoch, our validation accuracy is about 10% with a loss of about 2.33. After the second epoch, our accuracy is about 17%, and it is showing that the gradient at layer 2 is starting to become 0. Similarly, gradient at layer 1 is also starting to become 0 after the third epoch. The value of the gradient is decreasing. Okay. After the 10th epoch, what we can see is after the 10th epoch, the accuracy of our model is about 31%. The loss is about 1.88. The initial value of the gradients, as the initial value was set to 0, so basically it won't plot anything. After the first epoch, our gradient flow is like this. It is from layer 3 to layer 2 to layer 1. Similarly, after the 10th epoch also, we can see the value of the gradients that have been transferred. For as the number of layers is currently 3 only, so basically we won't see much of a vanishing gradient problem right now. So if we plot the loss of the model, it goes like this. If we plot the accuracy of the model, it goes like this, and it attains about 30%. Now similarly, we can see the functioning of 10H also. We just need to change the function to 10H. Now let's comment this thing and let's run our model on an increased number of layers with sigmoid as the activation. Now I have created a different model with more number of layers. So if I change the model, parameters will change. It is something about 3878122 number of parameters that need to be trained. The initial model accuracy is about 10%, which was same to previous. Now I will run this again. The learning rate is the TerraPass at about 0.01%, and SGD is used. So after the initial layer, the gradient at the level 0 becomes, the accuracy is about 10%. After second validation, the accuracy is about also 10%. Accuracy is not increasing much. So as we can see, after during the time epoch, the first initial value of the gradients was 0, as we have initialized it 0. That the first iteration, what we can see is at the third layer the gradient value is very much low. Similarly, after the first epoch, it becomes down and down, and after at epoch number 4 or 5th, the layer 4th weight are also starting to become very low. After 5th epoch, 6th, 7th, 8th, 9th, 10th. After the 10th epoch, or at the 10th epoch, we can see that the layers after the layer 4, at the layer 4 the gradients are becoming very low, so the updation of weights are not happening. This is basically what we call as vanishing gradient problem, and it works from 4, 3, 2 and 1. So basically layer 4 is from which the gradient is starting to decrease or the vanishing gradient is starting to appear. It is only this is only visible for 10 epoch. After, if we increase the number of epochs also, so it may be possible that after the layer the layer 5th and 6th may also be showing us the vanishing gradient problem. Now let's again change our model to the previous one and see it. Now change the model. Let's change the model's parameter. Let's change the model parameter from sigma to rel. I have again created the same model with the same number of layers, but this time I have changed the iteration function to rel. Model definition is created. This is the initial validation accuracy and the validation loss. I have also done this on the 10h function, so 10h is also showing the same thing. And now for ReLU, what I will do is I will increase the number of epochs to 50 so that we can see how it is working. And here it goes. It will take about 5 minutes to run the full 50 epochs, and we can see the results after 5 minutes basically. This is just a warning because more than 20 figures have been opened at the current time, so it is showing us a warning, right? of this output that are showing gradient 0 at layer 1 is basically the minimum value of the gradient at a particular layer. So basically we cannot say whether the gradient of a particular whole layer is 0 or not, but it is showing the minimum value of that particular layer gradient. And if it is less than 10 to the power minus 10, then it is showing the result of the particular layer. So after 50 epochs on a particular for the particular training, we have achieved an accuracy of about 48% with a loss of about 1.45%. And the gradient flow initially it is 0 because we have initialized the gradient 0. After the first epoch it is like this. After second epoch like this. Third epoch, fourth epoch, fifth epoch, 6th, 7th, 8th, 9th, 10, 11, 12, 13, 14, 15, 16, 17, 18, 23, 24, 25, 26, 28, 29, 30, 31, 32, 33, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49 and 50. So as we can see, after 50 epochs also, based on the same neural network architecture, if we change the activation function from sigmoid to ReLU, in sigmoid it was showing us an vanishing gradient at a 10th epoch only from layer number 4, but in ReLU even after 50 epochs we do not have any a sign of showing a vanishing gradient. For plotting the loss, we can see that the loss is decreasing, and for plotting the accuracy is increasing till about 45 to 50. In this way, ReLU is actually providing us much better accuracy, less loss, and it also solves the problem of vanishing gradient. So while using sigmoid and 10H, 10H is also providing us a very less accuracy of about 10% with something with an error of about something 2.4 to 2.6, which is much more, and it is also showing vanishing gradient. So in this video I have shown you how what is vanishing gradient, how it happens in sigmoid and 10H, and what is the solution of the vanishing gradient H, which is the use of ReLU activation function in case of sigmoid, in the place of sigmoid and 10H. Thank you.